Our sun. It gives us life. But it also holds the power to disrupt our world in ways we can hardly imagine. Imagine a massive explosion on the sun's surface. A surge of energy so powerful it could reach Earth in a matter of hours. These are solar superstorms, and they pose a growing threat to our modern way of life. Our technology, our communication systems, our power grids, all are vulnerable to the wrath of these cosmic events. Solar superstorms unleash a barrage of radiation and charged particles that can penetrate our atmosphere. This can disrupt satellites, interfere with radio communications, and even cause widespread blackouts by overloading power grids. The sun is a force of nature, both beautiful and dangerous. Understanding its power and our vulnerability to it is crucial for our future. The Earth itself holds clues to the sun's past fury. These clues are hidden in the most unexpected places, waiting to be discovered by those who know where to look. Scientists have found evidence of ancient solar superstorms by studying tree rings and ice cores. These natural archives provide a window into the past, revealing the secrets of our planet's history and the cosmic events that have shaped it. These natural records hold traces of radioactive isotopes, elements with unusual numbers of neutrons. These isotopes are like cosmic breadcrumbs, leading scientists to understand the intensity and frequency of solar activity over millennia. Tree rings, formed year after year, capture the composition of the atmosphere at the time of their growth. Each ring tells a story of the environmental conditions during that year, including the presence of radioactive isotopes deposited by solar storms. Ice cores, drilled from glaciers and ice sheets, trap atmospheric gases in layers that accumulate over centuries. These layers are like pages in a history book, each one preserving a record of the Earth's past climate and atmospheric composition. By analyzing these layers, scientists have discovered spikes in certain radioactive isotopes, such as carbon-14. These spikes are indicators of periods when the Earth was exposed to higher levels of cosmic radiation, likely due to solar superstorms. These spikes indicate times when Earth was bombarded by unusually high levels of cosmic radiation. This cosmic radiation interacts with the atmosphere, creating isotopes that are then captured in tree rings and ice cores. These spikes in carbon-14 serve as fingerprints of powerful solar storms that occurred long ago. By studying these fingerprints, scientists can piece together a timeline of solar activity and understand the potential risks of future solar events. They tell a story of past events that dwarf anything humanity has experienced in its short technological history. These ancient solar storms were far more intense than any modern event, reminding us of the sun's immense power and the need to prepare for future solar activity. Today, scientists use advanced technology to monitor the sun and predict solar storms. By understanding the past, we can better prepare for the future, ensuring that we are ready to face the challenges posed by our dynamic and ever-changing star. The study of tree rings and isotopes is not just about understanding history. It's about safeguarding our future. As we continue to explore these natural records, we gain valuable insights that help us protect our technology and infrastructure from the sun's unpredictable behavior. The next time you see a tree or a glacier, remember that they hold the keys to our planet's past and future. They are silent witnesses to the cosmic events that have shaped our world, and through them, we can unlock the mysteries of the sun's powerful influence on Earth. The sun, like all stars, is a giant ball of plasma, a superheated state of matter where electrons are stripped from atoms. This plasma is in constant motion, creating a dynamic and ever-changing environment. The sun's surface, known as the photosphere, is a seething mass of hot gases and plasma, with temperatures reaching up to 10,000 degrees Fahrenheit. Beneath this surface lies the convective zone, where hot plasma rises, cools, and sinks back down, creating a boiling effect that drives the sun's magnetic activity. This plasma churns and flows, creating powerful magnetic fields that twist and turn within the sun. These magnetic fields are generated by the movement of the plasma in the convective zone, and they extend far out into space, forming the sun's magnetic field. The sun's magnetic field is not uniform. It is constantly changing and evolving, with regions of intense magnetic activity known as sunspots appearing on the surface. These magnetic fields can become tangled and break, releasing enormous bursts of energy. When the magnetic fields become too twisted, they can snap and reconnect, releasing energy in the form of light, heat, and particles. This process is known as magnetic reconnection, and it is responsible for some of the most powerful events in the solar system. These bursts are what we call solar flares and coronal mass ejections, or CMEs. Solar flares are sudden, intense bursts of radiation that occur when the magnetic energy stored in the sun's atmosphere is suddenly released. CMEs, on the other hand, are massive eruptions of plasma and magnetic field that are ejected from the sun's corona, the outermost layer of the sun's atmosphere. Solar flares are sudden, intense bursts of radiation from the sun's surface. They can release as much energy as 1 billion megatons of TNT, and they can last from a few minutes to several hours. Solar flares are often associated with sunspots, which are regions of intense magnetic activity on the sun's surface. They are like giant explosions that release energy in the form of light and heat. The light from a solar flare can reach Earth in just 8 minutes, and it can cause disruptions in our communication systems, satellites, and power grids. The heat from a solar flare can also cause the sun's outer atmosphere to expand, increasing the drag on satellites and space stations. CMEs, on the other hand, are massive eruptions of plasma and magnetic field from the sun's corona, its outermost layer. These eruptions can contain billions of tons of plasma and can travel at speeds of millions of miles per hour. When a CME reaches Earth, it can cause geomagnetic storms that can disrupt our power grids, communication systems, and navigation systems. They can travel at speeds of millions of miles per hour. The fastest CMEs can reach Earth in just 15 to 18 hours, while slower ones can take several days. The speed and intensity of a CME can vary depending on the strength of the magnetic fields and the amount of plasma involved. While not all solar flares and CMEs are directed towards Earth, those that are can have significant impacts on our planet. When a solar flare or CME hits Earth, it can cause geomagnetic storms that can disrupt our power grids, communication systems, and navigation systems. These storms can also create beautiful auroras, or northern and southern lights, as the charged particles from the sun interact with Earth's magnetic field. Understanding these solar events is crucial for predicting and mitigating potential risks. Scientists use a variety of tools and techniques to study the sun and its activity, including satellites, ground-based observatories, and computer models. By studying the sun, we can better understand its behavior and predict when and where solar flares and CMEs will occur, helping us to protect our technology and infrastructure from their effects. Section 4. The Carrington Event, a glimpse into chaos. In 1859, the world witnessed the most powerful solar storm ever recorded, the Carrington Event. This monumental event was a stark reminder of the immense power of our sun, a celestial body that, while providing life-sustaining energy, also harbors the potential for catastrophic disruption. Named after British astronomer Richard Carrington, who observed the solar flare that triggered it, this event gave us a taste of the sun's potential fury. Carrington's meticulous observations on September 1, 1859, marked a significant milestone in the field of solar astronomy. His detailed sketches and notes provided invaluable insights into the nature of solar flares and their impact on Earth. Telegraph systems, the cutting-edge technology of the time, went haywire. These early communication networks, which were the lifeline of information exchange, suddenly became conduits of chaos. Messages were garbled, and operators experienced electric shocks as the telegraph lines became supercharged with solar energy. Sparks flew from telegraph wires, causing fires and disrupting communication across the globe. The intensity of the geomagnetic storm was such that telegraph systems continued to operate even after being disconnected from their power supplies, driven solely by the induced currents from the solar storm. Auroras, usually visible only at high latitudes, lit up the skies as far south as the Caribbean. These spectacular light displays, typically confined to polar regions, were seen in places where they had never been observed before, mesmerizing and alarming people in equal measure. The Carrington Event was a wake-up call. It underscored the vulnerability of our technological infrastructure to solar activity. This event highlighted the need for better understanding and preparedness for space weather phenomena. It showed us that even in the 19th century, a time of relatively simple technology, a solar superstorm could wreak havoc. The implications for today's world, with its intricate and interdependent technological systems, are profound. Today, with our world deeply reliant on technology, the consequences of such an event could be far more severe. Modern society's dependence on satellites, GPS, power grids, and communication networks means that a similar solar storm could lead to widespread blackouts, navigation failures, and significant economic losses. The Carrington Event serves as a historical lesson, reminding us of the need to safeguard our technological advancements against the unpredictable and powerful forces of nature. Section 5. Miyake Events. Echoes of Ancient Solar Fury. Even more powerful than the Carrington Event are Miyake events. These extreme solar superstorms, detected through spikes in carbon-14 in tree rings, are estimated to occur only once every few thousand years. The exact cause of Miyake events remains unknown. Some scientists speculate that they are caused by incredibly powerful solar flares or a series of major eruptions from the sun. Miyake events leave a distinct signature in tree rings, indicating a massive influx of cosmic radiation. These events are a stark reminder that the sun is capable of unleashing forces far beyond anything we have witnessed in modern times.